In this video, we'll look at Worksheet 5 that covers chapters 6 and 7. These were the confidence intervals, which we'll see in the first 7 problems, and then the rest of them are the hypothesis test that we saw in chapter 7. So, in the first question, we're asked for the margin of error given some particular values. So, we're given C, which is our level of confidence, so that's a 95% level of confidence. We're given sigma, which is the population standard deviation, and we're given n, which is our sample size of 120. Now, when population standard deviation is known, and this is going to be a common theme throughout from this point on, is that you'll be using z-scores. So the margin of error formula in this case is the z-score that you would get for that level of confidence. So z sub c is a value we'll find in our table F, and then the rest of the formula is to multiply this by your population standard deviation divided by the square root of your sample size. So we know two things. We can put 10.4 there, we can put 120 there, so we just need this z. And this is where we use table F. Technically, you can also use table E, the z-score, regular z-score table, but table F is just a nice place to go for most of the problems that we'll be seeing from chapter 6 onward. You would just look up the 95% level of confidence, that's the center column of table F, and then you go all the way down to the bottom, and you get that the z-score here is 1.96. So this is coming from table F, at the bottom of table F. So now you have that to plug in, and so you throw that in the calculator, you should get the answer here, A of 1.86. Now the margin of error is something that we would then add and subtract from the mean to get our confidence interval, which is what we'll see in the next couple of examples. In the next example, we have 40 students, so that's our N. Mean annual earnings, so that's X bar. And a population standard deviation of 677, so that's sigma. So that means, again, we'll be using this formula for the margin of error. And we're given, again, a 95% level of confidence, so the z is, again, 1.96. So we can plug all that in here to get our margin of error, and then we just add and subtract it from the 3120. That will give us our confidence interval that ended up being B. Next, the thing to look at here is how large a sample. So that means we're looking for a sample size, and the formula we have for that is basically this formula solved for n. So if you could try that out if you want some algebra practice, but if you solve it for n, you get zc times sigma over the margin of error squared. So that's our formula for the minimum sample size you would need to get a particular margin of error. So in this example, we're 90% confident. So this, again, using table F and going to the bottom, you would get 1.645. So that's the z sub c. Let me put that, z sub c is that. And we want to be within 2 ounces of the actual mean. So that means this 2 is our margin of error, E. And we're told that the standard deviation is 7, so this is our sigma. So we have everything we need to plug in. So when we do that, I think you get 33 point something, so remember, always round that up with these minimum sample sizes, so that rounds up to 34. Next, we're again finding a confidence interval, 95%. You might be thinking, oh, that's that 1.96 again, but not quite, because we're not told the population standard deviation. We're just told the sample standard deviation. Notice this is in the same sentence as the sample. So this is actually S. We are told the mean here, so that's our X bar, sample size of 16. And so in order to use table F here, we need our degrees of freedom, which comes from our sample size by subtracting 1. So we get 15 degrees of freedom. So from table F, you would get that your, oh, let me put the formula so that we know what we're talking about. So the formula changes slightly. Instead of Z sub C, it's T sub C, and instead of sigma, it's S. But then it's still divided by the square root of n. So the formula is almost the same, but we look for critical value slightly differently. We look at the 15th row of table F, and so we get T sub C in this case is 2.131. So now we have everything we need to plug in here. That gives us our margin of error, and then you would add and subtract that from the sample mean again, just like we did up here, to get our confidence interval, which ended up being B this time. Next up, we're looking at the proportion confidence intervals. Here we're just looking for a point estimate. That's what we call p hat. And so that's just your number of successes, x, divided by your sample size, n. And so in this problem, we had, this is our sample size, and this was our x, the number that said they own a car. So dividing those two numbers gives us our point estimate, which in this case was D. So about 34% own a car in this sample. Next, we want a confidence interval. So here we get yet another formula for the margin of error. This time it's back to a z-score, z sub c, so that's the bottom of table F again. And this part changes pretty drastically. It's p hat q hat, or square root of p hat q hat, all over n. So that's our margin of error formula for proportions. And the 90% level of confidence, that's actually the same as up here. It's a z-score again, so it's the 1.645 that you'll put in here. P hat, again, use this formula, so this is our x, this many that were veterans, and the total number in our survey. So dividing those two gives you p hat, and remember q hat is just 1 minus p hat. That equals 1 minus p hat. So plugging all that in here gives us our margin of error, and then adding and subtracting it from p hat gives us our confidence interval. So that one was D. Each of these confidence intervals could be done in the calculator. Let me point to the calculator function. So here it's the one prop z int. Over here is the t interval. And when sigma is known, you use the z interval. So those are all the calculator functions. You find those by first pressing stat and then going over to tests. And then you scroll down. I believe this one is the 7th one, this one's the 8th one, and I think this one might be A or something like that. And the final one from our confidence intervals is finding, and again, a minimum sample size. So remember how large of a sample is needed. So that means we're going to use a formula similar to this one, but this time you're taking this one and solving it for n. So again, if you want some more algebra practice, solve this equation for n, you get the formula for the minimum sample size for proportions, p hat q hat, and then the zc over e squared. So I need to locate these things. We want to be 98% confident. So again, using table F and looking at the bottom, that gives us a z-score of 2.33. I use that because if you look at the table, you get like 2.326 or something like that. But using that full number gives us slightly wrong answer here. Although you could argue, is it really wrong? At least getting the answer here, the numbers are far enough apart that you're not going to be too far off. But rounding does clearly affect things when doing any kind of statistics. So that's our z-score that goes in there. We don't want to be too far away from the mean. We want to be 3% away, so that means our e is 0.03. Be careful there, don't plug in 3 here. Make sure you change it to a decimal. And we're told that a previous study had the left-handed golfers at 10%, so that's our p hat. That's 0.1, and then so our q hat will be 0.9. If you're not given a previous study or anything like that involving p hat or q hat, just use 50% for each. So plugging all that in, you get 542 point something, so round that up to 543. And again, if you used the what was actually in table F, 2.326, I think you get 541 point something, and so that would round up to 542. But again, there's no number close to that here, so I think you would still conclude that it would be A. So just be careful with that. Rounding can definitely affect things here. Okay. Next we get into the hypothesis test. These first two questions are just asking for one step of the hypothesis test, so the test statistic. I'll also put that here. But in the first one, we're told the population standard deviation is 82, so that's sigma. So that means the test statistic uses the z-score formula, which is x bar minus population mean divided by sigma over root n, and we're given everything to do that, so we just plug everything into that, and you get A. And 9 is similar, but we're not given sigma, we're given S. So that tells us, that's the thing that tells us that we're using a T. Well, it also says it here, but if you didn't have that, the S would give that away as well. And the formula is very similar, x bar minus mu, but just replace the sigma with S. And just again plug everything in. I guess one thing that might not be given is what mu is, but like here it was told because that was our claim. But here we're said that the alternative hypothesis is that it's greater than 35, which would mean that the null hypothesis is less than or equal to 35. So that's still what your mu is. So 35 is what you'll plug in here. So that came out to be D. Okay. And the last of the multiple choice problems was to come up with a conclusion given some data. So we're either going to fail to reject or not have enough information. I suppose that's possible, although I haven't seen that actually as an answer in any of these multiple choice questions. Because, well, I guess something would have to be missing. Like if we weren't told any kind of standard deviation, then we wouldn't have enough information. Okay, so we first need to figure out what kind of test we're doing. We are given sigma here, so that is telling us that we are doing a z-test. And if we do this using the traditional method, we would first find our critical value. And it's similar to what we just did with the confidence intervals. If we look up in table F for 0.05, and since the claim is that it's greater than 21, this is a one-tailed, right-tailed test. So you look up one tail with 0.05, and then if you scroll to the bottom, you'll get this familiar 1.645 that we've seen a couple times now. So that's our critical value. That would be step 2 of the hypothesis test, finding, or the traditional method, finding step 2, or finding the critical value. And then we decide the test by whether or not the test statistic is either in the non-rejection region or the rejection region. So we need to find our z. Again, we're doing a z-test, so it's the z-score formula. So x bar minus mu over sigma over root n. And unfortunately I didn't write down what that is, but you have everything you need for it. Yeah, this is your mu, this is your x bar, sigma, and root n. So plugging all that in does give you a value that is in the tail, so it must have been bigger than 1.645, which means you reject the null hypothesis. Okay. Now, these next two problems where you're supposed to give a full hypothesis test, I do want to make clear, some of you probably noticed in your grades that you may not have gotten full credit for these problems because you didn't include all 5 of the steps. You only included a couple of the steps. Even if you had the correct conclusion, I still need to see that you did all the tests. Because remember, there's 2 answers here, right? You either reject or fail to reject. So if that's all I'm seeing, then it kind of feels like a guess. You had like a 50-50 guess of whether or not you're going to reject or fail to reject. So I do need to see everything leading up to that. So we'll start with a traditional method, and then in the second one we'll do the p-value method. Although you can use whatever method you'd like on any problem. So you could use traditional on all the problems, you could use p-value on all the problems. But I will show both so we can see them both. So the first step of any hypothesis test is to list the null and alternative hypotheses. So HO, or H0, and HA. The first thing you want to do is look at what the claim is and write that, in symbols and then place it in the right spot. So the claim was that the mean is less than 8. So that translates to mu less than 8. That would be an alternative hypothesis because of the less than sign. If it had the equal to, like if it said at least or at most 8 minutes, you would put the less than or equal to and put that as a null hypothesis. And the null hypothesis is just the opposite, so greater than or equal to 8. But we do list that the claim was that it was less than 8 minutes. So that's step 1, listing this down. In the traditional method, the rejection regions method, we would then find the critical value and draw a picture of what's going on. So the less than points to the left. So we would draw our distribution and put our tail on the left. So we're looking for this critical value. So in table F, we're doing a alpha 0.01. It's a one-tailed test. And we are told that the sample standard deviation is 2.1, so that's S. So that is telling us that we're doing the t-test. So that means we need degrees of freedom. So our n being 20 means that we have 19 degrees of freedom. So all that together, 0.01, one-tailed test, and 19 degrees of freedom, you can find that in table F to get your critical value of minus 2.39. Of course, table F only has positive numbers, so you have to choose to put the minus sign whenever it's a left-tailed test or a two-tailed test. So that's step 2, finding the critical value. And now in step 3, we calculate the test statistic, which again, it's a t-test, so we use the formula for t, x bar minus mu over s divided by square root of n. We have everything we need for that. This is the 6.7, this is 8, s is 2.1, and n was 20. So plugging all that in, we get a minus 2.768. And we can see that that is a bit less than minus 2.539. So that means we reject the null hypothesis. And finally, we interpret what it means to reject it. Rejecting always means that our data is statistically significant. So we would say that there is enough evidence and then whether we support or reject anything depends on what the claim is. So the claim is an alternative hypothesis, so we are supporting that claim because we're rejecting the null means we support the alternative, which is the claim. So we would be supporting the claim. And then you just briefly describe what the claim is. So in this case, that the waiting time's less than 8 minutes. technically should be the average waiting time is less than 8 minutes. But as long as you write something here, I'm fine with that. Okay, so again, for this worksheet, each multiple choice problem was worth 1 point each, but each of these were worth 5 points each. It was a total of 20 points. So if you didn't, each part was a point. So if you missed 3 of them, then you only got 2 points on this. I tried to give some partial credit, of course, but that's generally how I grade these. Okay. Finally, we're told a recent study claimed that at least 15% of junior high's students are overweight. So that is our claim, so we can start on step 1 here. But also we're talking about a percentage, so we know we're doing a proportion test. So this claim is that the proportion, P, of junior high students is at least greater than or equal to 15%, 0.15. So because of the or equal to, that's a null hypothesis. So we're going to put that here. And so the alternative is the opposite of that, so that the proportion is less than 15%. But we will be putting the claim up here. We have a sample of 160 students, so that's our N, and 18 were overweight, so that's our X. So we'd like to test this at a 0.05 level of significance. It says to use p-values. Again, you could have used the traditional test if you want, but I will show the p-values for this one, or the p-value method. So in the p-value method, the second step is to find the test statistic. For proportions, we go back to using z, and the formula here is different from what we've seen before. This is p hat minus p, which is similar to like the x bar minus mu. It's the sample thing minus the population thing. And then the square root on the bottom is pq over n. Be careful here. They're not hats, so this p is actually this p, or both of these p's are the 0.15, and so the q being related to that would be 1 minus p, so 0.85. So that's what you're going to plug in here. All right. But that gives you a minus 1.33 as a z-score. And then in step 3 is where we draw the picture of what that looks like. And being a left-tailed test means that our tail's over here. And then we put that kind of like a critical value, but not quite. Oh, sorry. But the p-value is the area in this tail. So there's a couple ways to do that. You could do the calculator with the normal CDF, do like minus 10 to minus 1.33 to get this area. But remember that table E, it kind of works best if you're looking for area to the left, because you can just look this number up and it'll immediately tell you this area. So in this case, it's, I'll just say the P. Make this a big capital P to distinguish it from the other P's. But this is the p-value, is 0.0918. Now to decide our test, we compare that to the alpha. So in the p-value method, you just compare the p-value you get from step 3 directly to the alpha that's given. So 0.0918 is bigger than 0.05, which means the probability of making a type 1 error is a little over 9%, and what we're willing to live with, or willing to risk, is a 5% chance of doing that. So because that's beyond that, or we would conclude that it's too risky to reject the null hypothesis here, so we fail to reject it. And then failing to reject, remember, rejecting always means that there is enough evidence. Failing to reject always means that there is not enough evidence, or that our data is not statistically significant. So that's how we'd start our sentence here. And this time the claim was the null, so there's not enough evidence to reject that claim. And then again, write briefly what that claim was, which was that at least 15% of the junior high students are overweight. All right. So again, one takeaway here, especially for the tests that are coming up later, and the future worksheets, do make sure that you include, whichever version you do, both have 5 steps, that you include all 5 steps so I can see them clearly. So each one always starts with the null and alternative hypotheses. The 2 middle steps, or step 2 and 3, depends on which one you're doing, but both of them involve finding some test statistic. The other one involves drawing this picture and either finding a critical value or a p-value. And step 4 is always your decision, either rejecting or fail to reject, and step 5 is writing the conclusion in words. So as long as you include all 5 steps, you should get all the points for that problem.